All right, so those are the three things that you want to make sure that you have before you do this binomial experiment. Repeated trials, the two possible outcomes, which we're going to call a success or a failure, and the probability remains the same throughout. That's correct. You cannot do things without replacement, because if you do something without replacement, then the probability won't remain the same. Okay? So you could draw a marble out of the bag, look at its color, and put it back. That would be okay. Okay, but you can't do things without replacement. All right. So with that, it says this: as part of a promotion, a store is giving away scratch-off cards. Prizes are awarded on 40% of the game cards. Suppose you have 3 cards. Find the probability that exactly 2 of the 3 cards will reveal a prize. And I said, make a tree diagram to help find the answer. So, here's what I'm going to do to get us started here. You've got 3 cards. So that means the trial that's happening is you're going to scratch off these game cards. And how many trials are you performing? 3. You're going to scratch off the first card, then you're going to scratch off the second card, then you're going to scratch off the third card. What's the probability of a success? And what do you think a success is in this case? Getting a success would be winning, getting a prize, right? What are the chances that you get a prize? 40%. Does that change from card to card? If you get a prize on the first card, is that going to affect whether or not you get a prize from the second card? No. Okay. So are they independent, so to speak? Yeah, because the probability of a success stays the same. So here's what I'm going to do for my tree diagram. Up here I'm going to say prize, and down here I'm going to say no prize. Okay? And the probability of getting a prize, you already told me, was 40%. Therefore, a no prize would be, okay, that's our card number 1. To get to card number 2, I could come off of either one of these branches, and I could either get a prize or a no prize. A prize or a no prize. Did the probabilities change? No, so it's still 40% for a prize and 60% for no prize. That's for my second one. Now, I need the third one. All right, so up here, I could either get a prize or no prize. And won't the probability stay the same? From here, I could either get a prize or a no prize. A prize or a no prize. And same thing here. Does everybody understand this tree diagram? How many possible outcomes are there when you scratch off these 3 cards? There are 8, right? You could either get prize, 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 or prize, prize, no prize, or prize, no prize, 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 no prize, no prize. Do you see how I'm reading this? There are 8 outcomes. There are 8 possible outcomes. We were asked to find the probability that exactly 2 of the cards will reveal a prize. So we want the probability of 2 prizes. How could I get 2 prizes? Okay, I could get a prize, followed by a prize, followed by a no prize. I could get a no prize, followed by a prize, followed by a prize. Okay, and finally a prize or a no prize, and then a prize. Aren't there 3 ways? Okay, how do I get the probability for this one? Look on your tree diagram. We did this the other day. If I want to do a prize, prize, no prize, what do I do with those 3 probabilities? You multiply them. So I'm going to do 0.4 times 0.4 times 0.6. What about for this one? It's pretty much the same thing, right? Except the 0.6 comes first. But does the order matter? No. So isn't this one also going to be 0.4 squared times 0.6? What about this one? Same thing, 0.4 squared times 0.6. So really what I'm going to end up with are 3 sets of 0.4 squared times 0.6. Do you agree? And that's 0.6 to the first. Do you agree? Okay. What does the 0.4 represent? It's the probability of getting a prize, but we called getting a prize a what? A success. Why do you think the probability of a success is being raised to the second power? Because I wanted 2 successes, didn't I? I wanted 2 wins. If I have 2 wins, then how many failures, so to speak, should I have? 1, because I only have 3 cards. If 2 of them are successes, doesn't that mean 1 has to be a failure? Do you see the exponent on the failure? The probability of a failure was 0.6. Its exponent was 1. Now, so I've got the probability of a success raised to the second, the probability of a failure raised to the first. The question is that coefficient of a 3. Why 3? There were 3 possible outcomes that I could get, and I can see that from the tree. The question is, where does that come from if I don't have a tree? Okay, it has something to do with the number of cards, right? I have 3 total cards, yep. And it's not the number of trials, because, well, I'm sorry, yes, it is the number of trials. The 3 is the number of trials. Isn't it the number of ways that I can arrange a prize, and a no prize? It's the number of ways I can arrange those. I could go P, P, no P. I could go P, no P, P. Or I could go, go ahead and laugh. And the last one, of course, okay? So there are 3 ways to arrange those, right? There are 3 ways to arrange those. If you think back to when we were doing our probability unit, do you remember when we were arranging letters of words? And we wanted to find all the different ways that we could arrange them? Was that a permutation or a combination? It was a combination. I'm doing a combination here, right? I'm doing a combination of how many things am I arranging? 3. And I want to look at groups of these 2. So take your calculators real quick and try 3 combination 2. What did you get? 3 combination 2, you should have gotten 3. Okay? This right here is essentially your formula for a binomial probability. Okay? Let's see if we can do this for receiving exactly 1 prize. Okay? From up on your tree diagram, for getting 1 prize, first of all, how many different ways could you get 1 prize? How many different paths could you follow? 3, right? Prize, no prize, prize. No prize, prize, no prize. Or no prize, no prize, prize. So there are 3 different ways again. For each of those 3 ways, what are your probabilities? Okay? 0.6 squared and 0.4 to the first. Why do you think 0.4 is to the first? Because you just want 1 success, right? Why do you think 0.6 is being squared? Because you're getting 2 failures. You're getting 2 losing cards. Where do you think this 3 came from? It's the number of paths up there, but what kind of combination is it? 3C1. Try 3C1. Is it really 3? Yeah. Okay. Do you see how this is working? Yes. On here, what is this matching up with? The number of successes that you want. Okay? And I'm going to write this all out for you right now. Okay? I was trying to show you with an example, but I don't want to have to make tree diagrams. So the binomial probability looks like this. NCX, P to the X, Q to the N minus X. Okay? That's your binomial probability. I'm going to tell you what all of these things stand for. N stands for the number of trials. X stands for the number of successes. P stands for the probability of a success. And Q stands for, that's right, the probability of a failure. If you want to write over here, N minus X will have to equal the number of failures, right? And what do you know about the number of successes plus the number of failures? If you want to copy that down. Yeah, they'll have to equal the total number of trials, right? Also, something else, the probability of a success plus the probability of a failure, do you know what that's always going to have to equal? 1. You either succeed or you fail. If there's a 40% chance you succeed, then what are the chances you fail? 60. Okay, if it's a 25% chance you succeed, then the chance that you fail is 75%. Okay? All right. So, do you have all of that down? Okay, let's do a few examples. So it says a calculator contains 4 batteries. With normal use, each battery has a 90% chance of lasting for 1 year. What is the probability that 3 of the 4 batteries will last all year? Okay, in this particular problem, what is it that we're looking at? What would you consider a trial? A trial would be, yeah, maybe battery life. We're looking at the battery life. Okay? So we're looking at the battery life for how many batteries? How many trials are we doing? We're doing 4. We're looking at 4 batteries. In this case, what is a success? What is it? Not how many. What is a success? Lasting 1 year is a success. Right? If you can identify it in words, a lot of times getting the number is pretty easy. So how many successes are we looking for? 3. What's the probability of a success? 90%. Therefore, what is the probability of a failure? 10%. If you've got this written down, you can do your probability because it says NCX. So we're going to do 4C3 times 0.9 to the 3rd. And the way I remember that is, how many successes do I want? I want 3 of them. So the exponent on the success has to be a 3. What's the probability of a failure? 0.1. And how many of those do I want? 1. There you go. Could you multiply that out? Okay, I'm going to let you do that. All right. I think this is the one that I want to look at next. This one says, one survey found that 80% of respondents eat corn on the cob in circles rather than from side to side. Assume that this sample accurately represents the population. What is the probability that out of 5 people you know, at least 2 of them eat corn on the cob in circles. Okay. At least 2 eat corn on the cob in circles. Okay. So first of all, what is a trial? Well, just a trial, not a success or a failure. A trial would just be eating corn. Okay? Okay. What would be a success in this case? I would say in circles, right? Eating in circles. Okay. You might want to pay attention to this one. All right. What is the number of trials in this case? 5. You're looking at 5 people that you know. Yes. I called that the success because that's what my probability was. Okay. Now, you could have called that a failure and called eating from side to side your success. It doesn't matter. Okay. As long as you're consistent, it doesn't matter. You'll get the same answer. Okay. Okay, so if we're calling a success eating in circles, how many successes do we want? Careful. What does it say? It says at least 2, which means tell me how many successes I could have. 2 or 3 or 4 or 5. It is. Although I'm going to have to do it how many times? 4. I'm going to do it once for the 2, once for the 3, once for the 4, and once for the 5. And once I do all of that, what am I going to do with all those probabilities? Add them together. I'm going to have 4 separate probabilities that I'm going to add together. Okay? What's the probability of a success in this case? What's the probability of a failure? Now, it sounds really bad, but it's not too hard because the first one is just going to be 5C2 times the probability of a success. How many successes do you want? Times the probability of a failure, and how many failures do you want in that case? 3. If you have 2 successes, you have 3 failures. Then the next one, all you're going to do is, this becomes 5C3, and now how many successes and how many failures? And then finally, yeah. Now, once you get all of these, you're going to add them all together. Okay? You will add all of those together and you will have your final answer. Now, there is a very slightly shorter method to this one because if you look at that list that I have compiled up there, that would be all of the successes except for which 2? 1 and I have 4 successes. 0, right? Another way that you could do this is find the missing 2 instead, the 5C0 and the 5C1, and then do 100% minus what you get there. It's a little bit shorter because you only have to do 2 instead of 4. Do you see that? So, okay. Then, here is your assignment.